Welcome to Metaphase Technologies. In this overview, we'll show what makes Linescan cameras different from the Areascan cameras we're all familiar with. We'll highlight common Linescan applications such as inspecting continuous sheets of materials or webs and sorting fast-moving discrete objects. We'll illustrate standard lighting techniques as they apply to Linescan, and we'll present a dynamic Linescan video. So let's get started. Both Linescan and Areascan cameras are used for inspection. They are similar in basic operation, but there are some important differences that make one or the other a more desirable solution depending on the application. A typical Linescan camera system is faster with higher resolution than its Areascan counterpart. It images only one video line at a time versus the two-dimensional area camera. Cost and complexity, however, are the trade-offs. Linescan and Areascan cameras use similar technology. A lens focuses light onto an array of photosensitive elements or pixels. The elements then transform the photons from the light into electrons. The camera's electronics then convert the electrical impulses into data that computer software can analyze and display. The main difference between the two is the form factor of the sensor. A Linescan sensor, as its name implies, has an array that is 1 pixel wide, while an Areascan camera has a two-dimensional array. Linescan cameras don't have the synchronization overhead of array cameras. Their high speed and resolution result from offload synchronization and processing downstream, so that their scan times are much faster, with rates of a millisecond or less that are common. To obtain a 2D image from a Linescan camera, the individual lines are combined, one after another. The height of the image is determined by the length of the sensor array, and the width is determined by the number and spacing of the lines, which are determined by pulses from an encoder or a controller. A typical linear array is 1 pixel by 8,000 pixels, with lengths of 16,000 or more increasingly common. These long sensors usually require a larger format f-mount lens. Our mobile phones are 2D cameras. They capture images of scenes and objects that we can readily see as pictures, with width and height. The incredible image quality from these devices is partly the result of high-resolution image sensors and partly from sophisticated image processing software specifically designed to compensate for the extremely tiny pixels. The image manipulation required by these small sensors make them impractical for machine vision. 2D cameras, with the larger image sensors, reduce lens distortion and are more sensitive to photons. Their design also often permits customization by camera manufacturers. For machine vision cameras, this means delivering raw video, with features such as variable scan, trigger, shutter, and more. The typical resolution is 2 megapixels from an array of approximately 1600 by 1200 pixels. The scan rate harkens back to the pre-digital video standards with 33 milliseconds, 30 frames a second, as standard, with other scan rates user configurable. For these cameras, C-mount or CS mount lenses are standard. Linescan cameras are ideal for continuous web inspection. Examples abound: glass, paper, fabric, plastic, and rolled steel. In these applications, the area to be inspected is relatively large, with typical widths of a meter or greater, and the material is moving fast and it doesn't stop. Because the width of these applications can be a meter or more, several Areascan cameras would be required to meet resolution requirements, and the high speed would necessitate costly lighting and camera scan configurations. A Linescan camera, on the other hand, delivers greater resolution across the web. The reduced scan time provides useful image data which is combined for downstream processing. Linescan is not limited to continuous web inspection, however. Fast-moving parcels, food products, and bulk solids are also good candidates for Linescan systems. In fact, any application involving continuous motion and high resolution deserves consideration for Linescan. A system's image quality only begins with the sensor resolution and superior optics. The illumination technique is critical to inspection performance. How light enters the camera, either directly or reflected from a surface, depends on the relative angles among the object to be inspected, the light source, and the camera. The angle of incidence equals the angle of reflection. This means that there is a position where photons emitted by a light source will be reflected by a surface directly to the camera. Variations from a smooth surface are detected as different light levels. Defects can be enhanced optically by positioning the light and the camera so that either the background or the defect reflects more light. For example, a small scratch on a sheet of metal will reflect light at a different angle than the surface and may appear either lighter or darker, depending on the angles. When both the light source and the camera face the same surface of the object, the configuration is said to be top or front lighting. Here, photons emitted by the light source are reflected from the object surface to the camera. The Metaphase UL-LL delivers a narrow, structured beam. Its high intensity and concentrated light make it ideal for the narrow field of view of a Linescan camera. Its high intensity and uniformity allow it to be used as a front light to inspect for material defects, angled to obtain an off-axis effect to highlight surface defects, or it may be placed beneath the object for a backlight effect to inspect for holes, voids, or contaminants. The UL line light is available in a wide variety of wavelengths and configurations such as monochromatic, SWIR, and hyperspectral. Some applications with highly reflective surfaces such as foil, plastics, or printed circuit boards may require an additional angle component to be designed into the light itself. In these low-angle lighting applications, the incidence angle is acute and the background surface appears dark as the light is reflected away from the camera lens, while irregularities are reflected into the lens and appear bright. The Metaphase MB-CLL uses proprietary optics to project its light at a lower divergence angle. This helps keep a tight, structured beam of light at a longer working distance, even many meters away, while delivering high intensity. The MB-CLL works great for applications where you can't have the light close to the object or web. When an object has holes to be measured or detected, it is often more effective to have the light and the camera on opposite sides of the object. This technique is called backlighting. The resultant image is a silhouette with very sharp edge definition. The Metaphase MB-BLL delivers a uniform brightness beam, making it ideal for detecting holes in continuous web applications. Thanks for watching our instructional video. Remember, Metaphase has a wide variety of machine vision lighting to fit almost any application, and custom solutions as well. Visit www.metaphasetech.com for a full view of their comprehensive product line, and look for other instructional videos on lighting theory, techniques, and applications. Thanks again.